very warm welcome to all the esteemed dignitaries and the distinguished guests gathered here today for the Professor Santappa and Dr. K.V.Raghavan Memorial Lecture 2025. And may I welcome the dignitaries to the dais, please. Dr. Ashish, Lele, Director, CSIR-NCL Pune, and Dr. P. Saravanan, Chief Scientist at CSIR-CLRI. Can we have a round of applause for the teachers? Thank you, sir. May I request everyone to rise for the Tamil Thai voices. Professor Santappa and Dr. K.V.Raghavan, of whose memory this lecture is instituted. I request Dr. P. Saravanan to felicitate our chief guest with an Ambavastham, please. I request Dr. P. Saravanan sir to welcome the august gathering.
A very good morning. Dr. Ramaswamy, former director of this institute and former secretary of DST, Dr. Chandrasekharan, former director, distinguished guests, colleagues, students and friends. It gives me great pleasure and privilege to extend a very warm welcome to you all to this Dr. Santappa and Dr. K.V.Raghavan Memorial Lecture. This annual memorial lecture is cherished occasion for all of us at CLRI. A moment when we come together to celebrate the lives and legacies of two of our most illustrious leaders, Professor Santappa and Dr. Raghavan. Both of them, through their vision, scholarship, and leadership, have profoundly shaped not only this institute, but also the larger scientific and technological landscape of our country. Professor Santappa was a pioneering polymer chemist and an institution builder who embodied scientific excellence in academic leadership With double doctorates from the universities of London and Manchester, he made seminal contributions to polymer science and chemical research in India. As director of CLRI from 1973 to 1981, he guided the institute through a period of remarkable scientific growth and institutional excellence. He later served with great distinction as Vice Chancellor of both Sri Venkateswara University and the University of Madras, nurturing generations of scholars. A recipient of S.S. Bhatnagar Prize in 1967 and fellow of several prestigious academies, Professor Santappa remains a beacon of inspiration. The Professor Santappa Award, instituted by the Society for Polymer Science, stands as a continuing tribute to his contributions to polymer chemistry. Dr. K.V.Raghavan, an eminent chemical engineer with a PhD from IIT Madras, joined this institute in 1986 and became its director in 1994. His tenure was marked by visionary initiatives that enhanced the institute's technological strength and external visibility. He founded two important divisions in this institute, namely the Chemical Engineering Department and the Cell for Industrial Safety and Risk Analysis, CSIR, that expanded CLRI's research horizons and industrial impact. Dr. Raghavan's leadership extended beyond the institute. As director of IICT Hyderabad and later as chairman of the Recruitment and Assessment Center, DRDO, he contributed immensely to national science and technology policy and governance. His many accolades, including the NIDMA Gold Medal, the NRDC Invention Promotion Award, the fellowships of several academies, bear testimony to his distinguished service to this scientific community. We are gathered here today to honor these two visionary leaders, to celebrate their enduring legacies and to draw inspiration from their lives dedicated to science, innovation, and national development. It is indeed our great privilege to have Dr. Ashish Lele, Director, CSIR National Chemical Laboratory, Pune, as the orator for this year's memorial lecture. Dr. Lele is among India's foremost chemical engineers, renowned for his pioneering work on polymer science, rheology of complex fluids, and sustainable materials. An alumnus of ICT Mumbai and the University of Delaware, he has seamlessly bridged academic research and industrial innovation. His numerous honors, including the S.S. Bhatnagar Prize in 2006 and the Infosys Prize in 2012, reflect his outstanding scientific leadership. As a fellow of INSA, IAS, and INAE, Dr. Lele continues to exemplify the very spirit of scientific excellence that Professor Santappa and Dr. Raghavan personified. We are truly honored to welcome Dr. Lele to deliver today's memorial lecture titled Molecular Topology to Industrial Processing of Entangled Polymers. On behalf of CSIR-CLRI, I extend my heartfelt welcome to Dr. Ashish Lele, to all our esteemed guests, colleagues, and students. I have no doubt that today's lecture will inspire us to carry forward the legacy of our great mentors with the same passion for scientific inquiry, innovation, and service to the society. Thank you all so much. Welcome, sir.
Thank you, sir. May I request our chief guest to deliver the memorial lecture, please.
very good morning to all of you. Dr. Ramaswamy, Dr. Chandrasekhar, Dr. Saravanan, thank you so much for being here today, and thank you for inviting me. It's a real honor and a privilege for me to give this memorial lecture in remembrance of two very, very distinguished scientists, scholars, educationists, people who were passionate about converting science into something meaningful, technologies that will be useful to mankind, and who also had I guess, the entrepreneurial instincts of one of them even starting a company. Both the gentlemen had, direct influence on the research that happened in the polymer science and chemical engineering at NCL. They were also involved in NCL in many different ways. Dr. Raghavan was on our research council, and his tenure led to many interesting discussions. I remember when he guided particularly the chemical engineering group at NCL. Professor Santappa is a visionary, and who in polymer science in India does not know Professor Santappa. The Society of Polymer Science of India has instituted the Santappa Award, and I'm very happy to say that 3 of our distinguished scientists, 2 ex-directors and a scientist colleague at NCL, have been honored with the Professor Santappa Award instituted by the SPSI. Also, Dr. Shivaram, who was the former director at NCL, was a core member of the team that celebrated the birth centenary year of Professor Santappa. So we have very fond remembrance of both Professor Santappa and Dr. Raghavan, and therefore for me it's a real honor, a real privilege to be able to give the memorial lecture today in this very wonderful hall and before such a distinguished and fantastic audience that I have. So I have particularly chosen to speak about an area that actually it's a little bit old work. This work was done somewhere around 2020, 2021. But I chose this topic because it has elements of 2 things which Professor Santappa and Dr. Raghavan sort of epitomized. One is polymer synthesis, and the other is chemical engineering, but of course applied to polymer science. I'm a chemical engineer by training, but my major has been in polymer science, and therefore I have this privilege of combining some bits of polymer science with engineering, and that's the topic I have chosen to talk to you about today. I must say that for the past 15 years, I have been a little away from this area. I have dedicated a lot of my professional time in the area of clean energy technologies and particularly in green hydrogen. We've done some very, very nice work that I'm particularly proud of in collaboration with many CSIR laboratories and in particularly in collaboration with CLRI, and I see 2 of my collaborators sitting in the audience today. And right from taking science in electrochemistry to developing technologies that are very close to commercialization, we've been doing a lot in the green hydrogen space. But along the sidelines, I have continued to work with a few PhD students and a few projects, continued to work on an area that I have been very much close to and enamored by, which is the polymer science and the polymer engineering part. And so for this lecture, I've chosen not to talk at all about the use of polymers in clean energy, but rather to talk about an area that I have been sort of following on the sidelines, which is titled here Entangled Polymers, and from molecular topology to industrial scale polymer processing. So that is the title of my talk. And it's really centered around commodity polymers. And these are basically polymers that we use in everyday life. There are polyethylenes, polypropylenes, polyethylene terephthalate, polyvinyl chloride. And you can see the numbers of the commercial production capacities of these polymers. And we're talking of 11 million metric tons per annum polyethylene, 7 million metric tons per annum polypropylene, and similar very large numbers. And these are Indian production capacities. The world production capacities are, of course, much, much bigger than this. So these are polymers which are produced in very large quantities across the world, and they are used in every single application that we encounter in our daily lives. It's today very, very difficult to imagine a day without the use of polymers in one form or the other. And a sample of some of the well-known applications of these polymers are shown there. And so the question is, how does one get from these polymers to these applications, and what is the science involved in it, what is the engineering involved in it, and what are the innovations that one can do? And what I'm going to talk about is one such example. So polymers are very big molecules. They are very linear, very long molecules. When we talk of polymers, we talk of tens of thousands of molecular weights. Typically, a polyethylene would be anywhere between 50,000 Dalton to several million Dalton. When I say Dalton, it's gram per mole. And these polymers come in a variety of molecular structures. As physicists and engineers, we think of polymers as long, snake-like or worm-like molecules, where you have the monomer segments, which are the basic building blocks of the polymers, joined to each other in a chain, more like pearls in a necklace. So you can have these very long linear chains, but you could have also other interesting molecular structures. We call them microstructures. And today's polymer chemistry is so advanced that you can make all kinds of molecular structures. You have linear polymer chains, you have polymer chains that have hair-like small chains coming out of it. These are called short chain branch polymers. You have some polymers that have very long chains sticking out of these polymers. These are called long chain branch polymers. And then you have other kinds of polymer architecture. You have star polymers, you have graft copolymers, you have brush-like copolymers, and a whole variety of polymer structures. So the polymer chemistry today is extremely advanced that allows you to engineer these kinds of molecular structures. In fact, you are slowly getting close to nature. You know, nature has wonderful ways of making polymers, and the modern synthesis of synthetic polymers is sort of getting there. So you are able to make all these wonderful microstructures. Now, what do these microstructures do? And you will see that the first thing that these molecular structures, these long chain structures do, is they give very interesting properties for flowing, for the flow behavior of these polymers. So on the top you will see a polymeric liquid in which you are simply stirring a rod, and instead of forming a vortex which pulls the liquid down, which is what we normally see in our chemistry wet labs, you take a polymer, it actually rises on top of this rod. It's called the rod climbing effect. And this is very unusual. The polymer is actually fighting gravity and going in the direction opposite to the gravity. In the bottom video that is playing, you will see a polymeric liquid that is extruding out of a die. And it's actually a liquid that is flowing, but you can cut it. You can cut it almost like a solid. And so it behaves like a liquid, it also behaves like a solid. When it extrudes out of that die, it actually swells. So the diameter of this polymer liquid is actually something like 150% more, 250% more than the die through which the polymer is being extruded out. So it has these very interesting, unusual properties, flow properties, and all of those properties are coming because of this long chain nature of the polymers. In fact, these are not some fancy polymers. The bottom polymer is actually low density polyethylene. It's a polymer that we use for making our milk pouches. Okay? So all these polymers show these very interesting flow properties. And so the question is, how do you measure these flow properties? And the science of measuring flow properties is called the rheology. The science of that is rheology. And on the top you see two equipments that are used in the laboratory to measure these flow properties. On the left is what is called a cone and plate viscometer. You have basically a flat plate, you have a cone, the liquid is sandwiched between the two, and one of them is rotated, either the cone or the plate is rotated. So you have the liquid which is sheared in between these two plates, and you measure the resistance to shear and convert that resistance into a property called as the viscosity. On the right, you have see two drums, and if I can play that video, there's a small video there. You will see this yellow squared box, which is sort of held between the two drums, and as the drums rotate, this film of material is stretched. You think it is a solid piece of material. It's not. It's actually a molten polymer mass. That film that you see is a polymer liquid. It's a melt. You heat it above the melting point of the polymer, and you can stretch that polymer film. These are not properties that you normally see for usual liquids like a water or an oil. These are very unusual flow properties of these materials. These properties are important because you have to take these materials and you have to pump them through a die. You have to mold various products that we use in everyday life. You have to mold these products out of these materials, and therefore you have to melt, flow these materials. You have to be able to take the pressure required to flow these materials, and for all of that, these properties, these flow properties become very, very critical. So when you do these measurements, you can get one of these various graphs that I have shown on the bottom, let's say something like a viscosity versus time. So imagine an experiment where I have taken this polymer liquid between these two plates, the cone and the plate, and I started rotating one of the plate, and I'm measuring as a function of time what happens to the viscosity. And so as you see, with increasing shear rates, the viscosity actually goes down. It of course rises, reaches a plateau, which is a steady state viscosity, and that steady state viscosity decreases as you increase the rate of rotation. The faster you rotate, the higher is the shear that you are imposing on the liquid, the lower is the viscosity. So these materials are what we call shear thinning liquids. They don't have one viscosity. They have a viscosity that changes with the rate of shear. Okay? The faster you shear, the lower is the viscosity you measure. The same material, when you stretch it, it behaves exactly the opposite. The faster you stretch, the higher is the viscosity that you will experience. Okay? And again, this is not a fancy material. This is low density polyethylene. Again, the polyethylene that is used to make our milk pouches or many other packaging materials. So depending on what kind of flow you impose on these liquids, whether it is a shear flow or a stretching flow, the material behaves differently. Sometimes it is shear thinning, sometimes it is extensional hardening, as we call it. So very interesting flow properties, and all of these flow properties come because of these long chain, interesting molecular structures of these polymers. Now, one of the key things that we need to understand, this is 101 on polymer topology, keep it very simple. These polymer, if you were to sort of zoom in and look at these individual polymers in the polymer melt, you will see that they look like a mass of noodles. You have these long chains embedded into other many long chains. So they are what we call entangled into each other, like a cotton candy. And these entanglements are very, very critical to the flow properties of these materials. What they do is they prevent each of these molecules to have large motions in directions which are orthogonal or transverse to the length of the polymer. And that is because the other entanglements are holding them. So these polymers can't move any which way they want. In particular, they can't move very easily perpendicular to the length of the polymer chain itself because they are constrained by the other polymer molecules. And these are called entanglements. So the way to understand these entanglements and their effects is to consider the bottom cartoon where you have these polymer segments between entanglements. So between two consecutive entanglements, the polymer is free to do what it wants. So it can move around, and typically these polymers, their Brownian part motions, they move around and form a lump. So those circles that you see there with the coil inside it are those lumps which are there between two consecutive entanglements. But at the point of the entanglements, it is constrained. It can't move around too much because it is fixed by these entanglements. And that's how the polymer molecule would look like. So if I have a polymer molecule now that contains n of these blobs, and each blob is of the size of, let's say, B, then n blobs times B size is the length of my polymer chain. So that's L. And then each of these blobs is moving in this constrained environment, and because it is connected with many neighbors, as it moves around, it encounters friction. Just like if you move around in a very packed vehicle, you will feel the friction around you. So these molecules are also in a packed environment, in an entangled environment, and they encounter friction. And that is called the monomer friction coefficient. Based on this very simple picture of a polymer in an entangled geometry, one can work out many interesting things. So if I can please play that video again. You see there one of these molecules, the white thread that I have shown in this molecule. Around it is these colored entanglements. And now what happens is these molecules, because of the entanglements, they can only move in and out of that tube. It's almost like a reptilian motion. It's like a snake or a worm that moves in and out of that tube. It's only when the molecule exits the tube that it can relax, because it has escaped the entanglements. And so if I take one of these polymer molecules and stretch it by applying a shear or by stretching it and then leave it, then the polymer has to relax back, because in an unsheared case, the equilibrium state of the molecule is to relax back into a more relaxed configuration. So how does it go from a stretched state or an oriented state into a relaxed state? And the way it does that is to escape through these tubes by a snake-like motion. Okay? That's the idea behind how these polymer molecules relax in an entanglement network. And so there is a diffusion coefficient for these polymer chains through these tubes. And let's call that DC. And of course, the longer the tube, the longer the polymer chain, the longer the tube, the more friction it will experience, right? So the diffusion coefficient scales inversely as the friction coefficient and the length of the polymer chain. How long does it take to escape the tube? For those who understand very simple physics, the time scale to diffuse out of the tube is roughly given by the square of the length of the tube divided by the diffusion coefficient. That's very simple scaling analysis. So the time to move out of the tube is called a reptation time. The word reptate comes out of the reptilian motion. So the time scale for reptating out of the tube scales as the square of the length divided by the diffusion coefficient. And if you do the math, you will see that this time scale scales as the cube of the molecular weight. And this is very important. What does it mean? It means that if you double the molecular weight, the time taken for the polymer to relax scales as the cube of 2. That's about 10, closely about 10. And therefore, if you double the molecular weight, it takes a much longer for the polymer chain to slowly relax from the stress that you have subjected the polymer chain to. It's a very slow relaxing polymer chains. Now what happens because of this slow relaxation? If I have stretched the polymer and I don't give it enough time to relax, this polymer is going to behave as if it is a solid, because it's not relaxing. Liquids are, which are always relaxed liquids. The molecules are always free to move. But here I have a polymer chain that is stretched and I'm not giving it enough time to relax. Before it can relax, I'm doing something else to it. It will behave almost like a solid. If I give it very long time to relax, it will flow like a liquid. And this is the reason why in one of the earlier videos you could see that I can take a liquid and I can cut it almost like a solid. Because the cutting motion is so fast that the polymer is not able to relax back, and therefore it behaves like a solid and I can cut a solid. I can't really cut a liquid. The typical liquids that we encounter in daily life, you can't cut a jet of water falling out of a tap, right? But here, a jet of polymer that is coming out of a tap, you can cut it because the cutting time is much smaller than the relaxation time of the polymer. And that is why we call this response viscoelastic. It has the viscosity of a liquid and the elasticity of a solid. And whether it is viscous or elastic depends on the ratio of the time of your process divided by the relaxation time of the polymer. If your process time is very short compared to the relaxation time, it behaves like a solid. If the process time is very long compared to the relaxation time of the liquid, it will behave like a liquid. These are preliminary important concepts because they will be useful throughout the remaining part of the lecture. Okay, and therefore now if you do this experiments of measuring the viscoelastic properties of this liquid, you're measuring two things, something called the G prime and the G double prime. The G prime measures the elastic part, the solid-like elastic part. The G double prime measures the liquid-like viscous part. You will see this interesting graph where on the x-axis of this graph is a frequency. That is, I am measuring how fast I am doing these motions. I can do them very slow or I can do them very fast. Depending on how slow or fast I do, and I measure the G prime and the G double prime, the elastic and the viscous part, I get a graph that looks like this. And this graph gives very interesting insights into the flow properties of the material. At very low frequencies, that is on the left side, frequency is the inverse of time. So very low frequency is very long times. So I'm giving enough time for the polymer to relax. And therefore, in this case, the polymer behaves like a liquid. The liquid response is the G double prime, and you can see on the left side, the G double prime, the liquid response is higher than the elastic response, which means the material behaves like a liquid. But at some frequency, they cross over. And beyond that frequency, it reverses. Now the elastic part is higher, the blue part is higher than the viscous part, which is the pink part. Which means now the material behaves more like a solid, because you're doing high frequency motions, that is, the time is very short, that time is not enough for the polymer to relax, and therefore you get elastic response. So you get a behavior that looks like almost a rubber. So on the left you get a flow response like a liquid, on the right you get an elastic response like a rubber. The material is the same, but depending on how you measure it, you get a viscous response or an elastic response. And there is one particular property that I will come back to during the talk, is the ratio of these two. It's called the tangent delta. It's simply the ratio of the viscous part to the elastic part as is shown there. And so in the left side, when you are flowing, the tan delta is greater than 1 because the ratio G double prime is higher than G prime, so the tan delta is higher than 1. On the right side, in the rubbery plateau, the tan delta is less than 1. Okay? So in later slides, I'm going to talk about tan delta, and you just have to remember that when tan delta is decreasing, it's becoming less than 1, I will get more elastic response. Okay. Now, when I take this polymer and want to make any products out of it, I have to mold it, or I have to flow it through a pump. So this is called polymer processing. This is industrial scale polymer processing. You extrude the polymer or you mold the polymer. And I've given two simple examples here. On the left is a standard process that we make bottles. All the PET bottles that you see are made by that process called blow molding. And you are basically extruding this liquid melt into a die, and you are pumping air to swell this liquid almost like a balloon. It actually swells like a balloon. And again, you will see in this process two things important. First, you have to flow the liquid. So it has to behave like a liquid. It has to flow out of a die into a mold. And when it enters the mold, you have to blow air in it, and it swells almost like a rubber, right? Like you can blow a rubber balloon. This liquid will actually blow into a bottle. So it has, in industrial scale processing, you see that it has to behave like a liquid in one case and an elastic liquid in the other case. Similarly, on the other side, there is a process called film blowing, and here this is a process by which you make films, and all the packaging films that you see today are made by this process. So again, the bottom red thing that you see is a pump. It's a pump for pumping high viscosity fluid into a die. So that's a liquid-like behavior. And once it comes into the die, which is the central part that you see, you actually blow air into it, and this liquid blows like a balloon. And at industrial scale, these are mind-boggling scales. A typical balloon of polymer melt can be as big as half a meter. Okay? And so these huge balloons, and they climb 3 stories tall, and that's how you make millions of tons of plastic films, which go into making your packaging material. So again here, it has to flow in the extruder, that's a liquid-like flow, and then it has to blow like a rubber balloon, and it's the same melt that blows into a balloon. So again, viscous elastic parts are very critical for industrial scale polymer processing to make products out of it. Now once you make these products, another interesting set of things come up. All the commodity polymers that I talked about, not all of them, but the polyethylenes and polypropylenes and the PET, they can crystallize. And polymers crystallize in very, very different ways than a low molecular weight species. And because they are these long chains, what happens is as the polymer melt cools down, these long chains start to fold. And they fold and pack into a crystalline lattice. So on the right you will see a chain that is folded and it packs into a crystalline lattice. And when they pack, they form beautiful lamellae, thin films of packed chains. And these lamellae will fold out from a nucleation center to form what you see on the left, which is a simple birefringent image of the polymer melt after it has solidified. And these are called spherulites. Okay? So you see these beautiful polymer crystals, but they are not really 100% crystals. Because in between the two lamellae, you have a mass of polymer chains which are entangled and which are amorphous. They don't have order in them. So polymers are typically never 100% crystalline. They are always semi-crystalline. Typically about 40%, 50% is crystalline. The remaining 40-50% is amorphous. And that's why they are called semi-crystalline polymers. And both this property, the amorphous and the crystalline properties, are absolutely important for polymer applications. This is exactly why you can stretch polymer films. They will not easily tear. You need both the crystalline part to give the rigidity and the amorphous part to give the ductility. Because of these wonderful properties, polymers are so widely used. Okay? The age of polymers has come because of these superb properties that are in the melt state as well as in the solid state. And therefore, if one wants to understand really the entire gamut from molecular structure to industrial scale processing, you have to really understand the structure property processing relationship. And so at the right side, you have the polymer microstructure, which leads to the flow properties that I talked about. These flow properties are important for processing the polymer at industrial scale. Once you make the products, they crystallize and they form these interesting semi-crystalline structure. And it is this structure that gives the properties, the rigidity, the ductility of the polymer. And it is these properties that ultimately, for all of us as consumers, we think these polymers are great materials. The performance of these polymers is wonderful. Now you can imagine that this whole structure property relationship here is essentially a bridging of length and time scales. The polymer molecules are a few angstroms up to a nanometers in size, and the films that we use are several meters in width. So you're going from nanometers or angstroms to several meters. So you're bridging length scales. The relaxation time of a polymer is maybe half a second, but the lifetime of a polymer product is years. So you're going from time scales of few seconds to few years. So it's really the game of understanding the bridge between length and time scales. And if you understand this structure property relations thoroughly, you can make products of the performance that you want, and that is why companies get competitive edge. So structure property relations in polymers, like in any other materials, is central to the competitive advantage of the polymer industry. So in today's talk, with this background, I'm going to talk about one particular story, a particular work that we've done more recently on blending high-density commercial polyethylene with a very unique polyethylene, which is called ultra-high molecular weight polyethylene. I'll tell you more about this as we go along. So UHMWPE is ultra-high molecular weight polyethylene. And what do I mean by ultra-high? The molecular weights are anywhere between 2 million to 10 million molecular weight. So very, very high molecular weight, very long polymer chains. In fact, they are so long that you can individually see polymer chains in a transmission electron microscope. They are just very long. They have very high strength. In fact, many hip joints that are used today in surgeries are made out of this ultra-high molecular weight polyethylene. Knee joints are made out of ultra-high molecular weight polyethylene. There are many, many applications of this wonderful polymer because they have very high abrasion resistance. On the other hand, you have high-density polyethylene, which is a commercial polyethylene produced, as I said in my first slide, in several million tons per annum. And one typical application of high-density polyethylene are pipes. And you go in any city, any metro, you traverse the length and breadth of this country, you will find thousands and thousands of kilometers of these high-density polyethylene pipes which stretch across the country, and they transport water, they transport natural gas, they transport crude oil, all very important materials. So both these materials are extremely important materials, commercially important materials, and they have these very important applications. Now, we were interested in looking at what happens when you start blending these two. So they are both polyethylenes. Chemically, they are similar. The difference is their molecular weight. One is about 2 lakh up to 5 lakh molecular weight. The other is an order of magnitude higher, 2 million, 5 million molecular weight. Okay? So what happens when you start mixing them? So remember this experiment that I said, you take a film, you melt it and you stretch it by wrapping around 2 drums. That's just a simple experiment. Essentially, you are stretching the film. Now, if I start putting a little bit of ultra-high molecular weight polyethylene in a lot of high-density polyethylene, and then start this stretching experiment, I see that with increasing amount of ultra-high molecular weight, the ability to stretch the film increases. I have to apply more force to stretch the film, and it also retains quite a bit of its ductility. So you get very interesting and important properties. If I want to make a film which is tougher, which needs more, which can survive more strength, needs more strength, I can dose a little bit of the high molecular weight polyethylene into the low molecular weight polyethylene. And these are not very high percent, they are less than a percent. Okay, less than a percent, maybe less than 5% of the ultra high molecular weight into 90+% high density polyethylene. Now you can make these blends by many different technologies. I can have, for example, 2 different reactors, make high density polyethylene in one reactor, ultra high molecular weight polyethylene in another reactor, and mix them in the reactor itself. I can have 2 different catalysts. One makes high density polyethylene, the other makes ultra high molecular weight polyethylene in the same reactor, and I will get a blend coming out of the reactor. But these are little difficult to do commercially. A much simpler way of doing this would be simply mix them. You make them separately in 2 different reactors, 2 different places, even 2 different industries, and then mix them by simply flowing them into a pump. Mixing is far more simpler than having fancy catalysts that can do different polymerization. So the question we ask ourselves is it possible to take an ultra high molecular weight polyethylene and mix it with a high density polyethylene? And the first thought is that should be pretty simple because both are polyethylene. Why should it be so different? It's like mixing one oil into another oil or colored water into a non-colored water. Right? It's a no-brainer that they should mix Why should it be any difficult? But this is where interesting things happen in polymer because they don't behave like normal liquids. So first of all, there are no thermodynamic barriers for mixing because they are both chemically the same material. They are both polyethylene, right? So thermodynamically, there is no barrier for mixing at all. But there are two important kinetic barriers for mixing. The first is dispersion. So if I want to mix one thing into another, the one that I want to disperse, I will try to break it into small pieces and then mix them. And hopefully because of the small pieces, it will mix faster. So that is dispersion. So the yellow colored on the right hand side is my high density polyethylene, which is my matrix phase. And the blue colored strip is these small particles of ultra high molecular weight polyethylene, which is dispersed. And I hope that these blue things will dissolve, right? Dissolve in the matrix. The first problem we encounter is because the viscosity of these two things is so different that it is not even possible to disperse them. If I take ultra high molecular weight polyethylene and try to shred it into pieces in a melt state, it doesn't happen at all. Okay? And there's some beautiful physics there that I won't talk about, but just take it for granted that an ultra high molecular weight polyethylene molten is very, very difficult to break into droplets. So dispersion is simply not possible. The second part is even if I were to disperse it, how long will it take for dissolution? How long will it take for the ultra high molecular weight, very long chains to diffuse out of their particles and dissolve? It's a diffusion process. And because the molecular weights are so large, and I remember I told you that they have to reptate in and out of the entanglements, and the reptation time scale as the cube of the molecular weight. So if I have a 10 million molecular weight or a 3 million molecular weight polymer, it is going to take, weeks for it to actually reptate out and dissolve. And no industry will have weeks to wait and dissolve things. You have to do them within minutes, not in weeks. And therefore, this is an interesting bit. You are mixing two chemically identical materials, but it's very difficult to mix them. Almost impossible to mix them because of these two barriers. So how do we cross this barrier? So our novel approach starts with the polymer chemistry. We say that what was the problem? The problem was entanglements. Entanglement was my headache because entanglements cause these long times of relaxation and all that. What if I don't entangle at all? Can I have a polymer chemistry, a new catalyst that makes disentangled polyethylene? And so it's a very interesting chemistry that we did where the polymer is synthesized in a reactor under dilute conditions, and as the polymer chain forms, it crystallizes within the solution and precipitates out. So before it entangles, it precipitates out. Okay? So what you see here is the C is the center of the catalyst on that cartoon, and as the polymer chain is building from the catalyst, it folds, crystallizes and precipitates out. Before any entanglements can happen, or you minimize the number of entanglements. You can never completely get 100% disentangled material, but you can minimize the number of entanglements by this technique. So we actually made very new catalysts which are patent protected. This catalyst has a titanium 3 Ti3+ center, which is the active center to make this kind of high density, ultra high molecular weight polyethylene, which is disentangled. How do we know that it is disentangled? We do a differential scanning calorimetry. We basically measure the melting temperature of this polymer. If you have a disentangled polyethylene, it will almost form single crystals of polyethylene. And single crystals of polyethylene have an equilibrium melting point of about 144 degrees centigrade, 144, 146 degrees centigrade. But if you have entangled polyethylene, which can't form single crystals, its melting point is lower. It's about anywhere between 118 degrees to 135 degrees, anywhere in between, depending on how far away from equilibrium it is, how entangled it is. So we trace this melting points, which is shown on the left, You see two melting peaks. The one on the right, with the two arrows, the one on the right is the single crystal melting peak, about 144 degrees. The one on the left is the non-equilibrium melting peak, about 135. The presence of these two peaks tells me that there is a part of the polymer which is disentangled. If I anneal it, that is, if I leave it at above its melting temperature for a sufficiently long time, this disentangled part slowly starts entangling, and this 144 degree peak moves to 135, and you can see as you go down, what the right side peak disappears and the left side peak becomes bigger. And so we can see from this thermal behavior that the polymer actually starts as a disentangled polymer and slowly starts entangling. Why does it entangle? It entangles because that is the equilibrium state. That is the state where the polymer is the most happy, okay, in the lowest free energy state. And therefore the disentangled state is actually a metastable state. It's a non-equilibrium state, and as you anneal it, it moves to the equilibrium entangled state. How do I know this? I can actually track it by using rheological measurements. So I take this polymer and I do this shear measurement, and in this case the cone or the plate is oscillated. It is not moving continuously, rotating, it's actually oscillating. And I measure the viscoelastic properties, and I see that if I take a conventional polyethylene, which is the top red, which is highly entangled, the viscoelastic property slowly increases. Notice that the x-axis is a log axis, so it takes quite a bit of time. It slowly increases and reaches a plateau. Now if I take my specially made disentangled polyethylene, the viscoelastic property is much lower because it is highly disentangled, so it is free to move. Less entanglements means the viscosity is going to be lower. So it has a lower viscoelastic property, but it does eventually grow and reaches the same equilibrium state. So the synthesized polymer as it comes out of the reactor is a metastable disentangled polymer, and as I equilibrate it thermally, it goes into the entangled state. But here is the interesting thing. If I look at how long does it take to reach the entangled state, it's about at least 10 to 15 minutes. So I get this interesting window of 10 to 15 minutes in which the polymer remains disentangled largely. And disentanglement is good because entanglement was my problem for mixing. If I can keep it disentangled for about 10-15 minutes, in that disentangled state, I can try to mix or dissolve the ultra-high molecular weight polyethylene, which is this polymer, into the high-density polyethylene, which is what I set out to do in the beginning. Okay, so how do I track this dissolution of disentangled polyethylene into high-density polyethylene? I can't use microscopy, spectroscopy, or scattering because chemically they are the same materials. I have no difference between them. Neither refractive index is different, nor any spectroscopic signals are different. I can't use the standard ways to track whether the high molecular weight, ultra-high molecular weight polyethylene disentangled is actually dissolving in the HDPE. And therefore, I use rheology as a way to track this disentanglement process. Why can I use rheology? Again, I come back to this point that for an entangled polymer, the time for relaxation scales as the cube of the molecular weight. So if I have a very long chain, it is going to relax much, much slowly compared to the high density polyethylene. They have very different relaxation times. So if I can measure them, then I can track how much is dissolving into the other. And the simple way to measure them is that ratio, the ratio of the viscous part to the elastic part, the G double prime to the G prime. If I track this property, then I can start measuring the dissolution. And remember, as it dissolves, as the ultra-high molecular weight polyethylene dissolves in the high-density polyethylene, this ratio is going to decrease because the denominator, which is the elastic part, is going to go up with the dissolution, and the numerator, this viscous part, is going to come down. So the tan delta is going to decrease. Okay, so how do I mix them? It's a very simple experiment. I have a small pump, a mixing device, which is shown on the top there. It is simply a cavity in which I have two rotating screws. I can't, the pointer doesn't work. So there are two screws there. I put my high density polyethylene and the ultra high molecular weight polyethylene in that device. I rotate the screw, wait for some time, and then take the material out. I rotate it at different temperatures with different speeds of rotation. I do it under nitrogen atmosphere so that it doesn't degrade. And then I take the sample out and I measure the rheology of it. I measure that tan delta that I talked about in the previous slide. Okay, so here is how it looks like. So on the left is the tan delta. On the x-axis is the frequency of rotation. And the top curve that I'm showing now is just polyethylene, the high density polyethylene, the matrix material. And that's the tan delta. And now I'm going to start adding the ultra high molecular weight polyethylene and see what happens to the tan delta. So here is 0.1% ultra high molecular weight in polyethylene, and you can see the tan delta coming down. Okay, and I expect the tan delta to come down because as the very long chains dissolve in the shorter chains, the thing becomes more elastic, and so tan delta starts coming down. So the fact that it is coming down tells me that some dissolution is happening. Now, if I take the disentangled, this is what I get. Suppose I take the fully entangled ultra high molecular weight polyethylene, okay, which is, I know is not going to dissolve very easily. What happens to it? The red one is the fully entangled ultra high molecular weight polyethylene. The tan delta doesn't move at all, which means the fully entangled species is not dissolving. And I start doing these experiments for higher and higher loadings of ultra high. So going from 0.1%, 0.5%. Again, with entangled it doesn't move, but with disentangled it has come down. 1% has come down more. Entangled doesn't come down at all. 5% has come down significantly more. 10%, again 10%. Entangled doesn't move at all. 30% has come down. So with every bit of addition of the disentangled ultra high, the tan delta has come down, and I know that the dissolution is happening. So rheology gives me a very nice and a simple way to track the dissolution of ultra high into high density polyethylene. I can now look at what happens to what is the effect of mixing time. Suppose I mix for 5 minutes or I mix for 30 minutes, what happens? And I'm not going to read through all this slide, but you can trust me that with higher mixing time, more dissolution happens as would be expected. But interestingly, not that much. Not that much higher dissolution seems to happen with increasing mixing times. But if I look at the effect of shear, I see that with increasing shear, a lot more mixing happens. Okay, a lot more dissolution happens. So shear is actually helping to dissolve the ultra high molecular weight into the high density polyethylene, which is actually very, very good news. Now, what is the whether shear is more important or mixing time is more important is seen from this graph, which I will show you. So the top curve is your mixing for 30 minutes at 30 rotation speed, 30 RPM for 5 minutes. And then instead of 5 minutes, you extend to 30 minutes. The red curve goes down. And instead of 30 RPM, I go to 150 RPM, but only 5 minutes, and I get the same tan delta. So whether I mix for 5 minutes at higher speed or 30 minutes at lower speed, I get the same value of tan delta, which means that I can actually use shear as a very effective way for mixing ultra high polyethylene into high density polyethylene. And this is great news because in industrial scale processing like an extruder, I can get very high shear, which is very helpful. But I don't have enough time because when I put the material in an extruder, within 3 to 4 minutes it comes out of the extruder. So within a short time period, but with high shear, I can effectively blend, dissolve the ultra high molecular weight polyethylene into the high density polyethylene. And that's where industrial compounding becomes exciting. So far, what we have is that the entangled ultra-high molecular weight polyethylene does not dissolve because of its very high degree of entanglements. But the disentangled polyethylene, the DEE, dissolves quite nicely in the high density polyethylene because of its lower entanglements and its metastable structure. Just about 5 minutes is enough, provided I give it sufficient shear forces, and therefore in an industrial compounding such a blending is possible. The second question, which I am going to skip through because I have already exceeded a lot of time here, is how do we actually quantify? So far I have told you that it mixes, but I have not told you how much mixes. Everything that I have put in, like 1%, does all the 1% dissolve or only fraction of that 1% dissolve? Can I quantify that? Again, I can't use microscopy, spectroscopy, nothing else can be used. I only have to rely on rheology as a tool to quantify how much of the ultra-high dissolves in the high-density polyethylene. And this requires a lot of theory. This requires a lot of understanding of the rheology of the polymers. The rest of the slides are a lot of theory, so I'm going to skip them. But this is quite complex theory, and it basically looks at predicting the viscoelastic properties. The third point here, the third bullet point, prediction of viscoelastic properties, which is the G prime and the G double prime for a blend of high density polyethylene and ultra high molecular weight polyethylenes. How do we predict them from individual properties of the two polymers and the weight fractions that are blended? Okay, if I can get a theory that relates the blend properties with individual properties, knowing how much is mixed, then I can fit this theory to the experiment and extract out how much has actually dissolved. The assumption here is that, that's the first bullet point, the assumption here is that only the dissolved quantities affect the rheology. The undissolved quantities does not affect the rheology, and I showed in my tan delta experiment that that is indeed true. The entangled ultra-high did not change the rheological properties, but the disentangled ultra-high, because it dissolves, brings down the tan delta. So only the dissolved polymers actually change the rheology. So that's a reasonable assumption to make. And so what we do now, what we've done now is to go back to the drawing board, go back to fundamentals, and understand how the chain dynamics, the motions of these chains affect the rheology. Okay? And I will only look at this, tell you only these simple things and not get into the math. There are three important Brownian motions of the polymers that are important to understand. The first is the reptation motion, the reptilian motion that I talked about. We have these polymers which are entangled, they form a cube, and the polymer only has to move like a snake in and out of the tube. That's the reptation motion. And it's a fairly long time scale. It takes a long time to escape the tube and relax. That's the reptation motion. It's a slow dynamics. Now, if you look at the polymer chain that comes out of the tube, once it has escaped the tube, it is free to move around. It's a Brownian particle, it's free to move around. And that is what is called the counter length fluctuation. You have a polymer chain which is unentangled, it has escaped the entanglements, and you have to look at motions which are there for unentangled polymers, and those are called Rouse dynamics, and they're very fast dynamics. They're basically polymers which are doing this kind of motions, beads in the polymer that are moving this kind of motion. And the third is a two-body problem. The third motion is a two-body problem because it's not one chain, you have an entangled chain with it and both are moving. So if one chain is smaller than the other, this is the fact in this case because you have a very high, ultra-high molecular weight polymer mixed in high density, which is much lower, 10 times lower molecular weight. So the tube of the ultra-high is formed by smaller chains. If the smaller chains move out, then the ultra-high is able to relax faster. Okay? So the tube itself relaxes before the polymers can relax. So the tube helps the polymer to relax. That is called constrained release. It's a two-body problem, and that actually accounts for the effects of polymer dispersity. Now the physics of this is quite complicated. There are a lot of math equations here which I'm going to skip, but I'm telling you that all that physics is derived from this understanding of the Brownian motions of these polymer molecules. And these Brownian motions were first proposed by two absolute genius, Pierre Dijon and Sir Sam Edwards. Pierre Dijon won the Nobel Prize for this discovery, and Sir Sam Edwards was the first one to actually conceptualize it. Unfortunately, didn't get the Nobel, but he wrote a marvelous book that captures all this beauty of polymer physics, these motions in the mathematical formalism. So you'll see all these kinds of equations that describe the viscoelastic properties to the relaxation modes of the polymers, and I'm going to skip all of that. You have to trust me that these theories actually work. Okay, and so now we look at the first comparison between theory and experiment. So these are individual polymers. The top left is high density polyethylene, which is the matrix phase. The bottom right is the ultra high molecular weight polyethylene, the disentangled ultra high molecular weight polyethylene, which is the dispersed phase. And these are individual polymers. The points are the experimental data measured, and the lines that go through the points are the theoretical fits. So all those very complex equations that I skipped actually do a wonderful job of predicting the rheological data. And this data has come out of the complete distribution of molecular weight that comes out of a the gel permeation chromatograph. So the insets are the GPC curve, the gel permeation chromatograph data, which actually shows the molecular weight distribution. We have used that distribution in the theory to predict the rheological behavior. So the theory actually does a very, very good job of this. You can see that the behavior, the G prime and the G double prime in these two cases is very different. The high density polyethylene, the blue data is on the top of the red data. The blue data is the viscous part. The viscous part is dominating than the elastic part. But exactly the opposite in the ultra high molecular weight polyethylene. The red data is up, the red data is the elastic part, and the blue is the viscous part. So the very high molecular weight polymer behaves like an elastic solid. That is the dispersed phase, and the high density polyethylene behaves like a liquid, as one would expect. Then we look at these blends, the blends of these two. We take all the theoretical equations and we actually now combine the theory and the experimental data. So now these are blends. In each of these figures, the square at the bottom right tells you how much disentangled polyethylene we have actually put in the mixing device. The square on the top left tells you how much of it actually dissolves. And this has come out of the theory. So if I take 1% disentangled polyethylene, I put it in, mix it with 99% high density polyethylene, I mix them and hope that some of it dissolves. How much dissolves, the theory predicts, is hardly 0.016%. Out of that 1%, a very small fraction actually ends up really molecularly dissolving. And you will see the same things for almost all others. So for example, the bottom right, I'm putting as much as 10% disentangled polymer and only 0.35% really dissolves in the matrix phase. But look at the rheological changes. These measurements are done at the same temperature, but there's qualitatively different graphs that you will see. So even a tiny amount of that disentangled that dissolves in the high density polyethylene, the rheological behavior significantly changes. Right, and so this table at the left summarizes the entire data. The first column is how much DPE actually I have added. The middle column is how much is dissolved. And the third column is the ratio between dissolved and added. And you'll see that really a tiny amount of what I have added actually dissolves. But that tiny amount has qualitatively changed the flow behavior of the polyethylene. And that's because the ultra high molecular weight polyethylene, gives spectacular changes to the rheological behavior. So spectacular that in a stretching flow, just the polyethylene doesn't undergo any extension hardening, but to put a tiny amount of the ultra high molecular weight polyethylene, the extension behavior completely changes, as shown at the bottom right. The bottom line, the blue line, is just polyethylene. You'll see how low it is. The top curves are when you add tiny amounts of the disentangled polyethylene to it. The viscosity goes up by orders of magnitude because the y-axis is a log scale. So the viscosity goes up by orders of magnitude, and also this graph that shows up, the extensional hardening, is a qualitatively different behavior. And so what I've shown you is how one story of how molecular structure changes the rheological properties. The rheological properties changes the performance of the plastic during processing, and these wonderful theories that have come out from the polymer physics domain give a very nice conceptualization of what is really happening. And in this particular case, no other experimental characterization will work to understand this dissolution. It's only the flow behavior, the rheology, that understands the flow behavior of this blend. So what we are doing now is to move away from the liquid state properties to solid state properties, and that's work under progress. And we are now trying to see how the solid state properties change. So I want to end by acknowledging firstly two gentlemen, Ajit Mathur and G.K. Rao from Reliance Industries. And I want to acknowledge them because they were the first to come to us saying, hey, this is an interesting problem. Can we look at mixing tiny amounts of disentangled ultra-high into high-density polyethylene? Because, it seems to do something very interesting. We don't know why. We don't know why, we can't quantify it, but it seems to do something interesting. It seems to change the properties of the high-density polyethylene significantly, and we as industry are very interested in it. It's of interest to them because less than 1% of the disentangled polyethylene, when dissolved in 99.9% high-density polyethylene, significantly changes the properties of high-density polyethylene. Okay? So this is of great interest to the industry. So they came to us, and this whole research started with a problem definition coming from the industry. I'm grateful to my colleague Samir, who is a polyolefin chemistry expert, and he actually synthesized the disentangled ultra-high molecular weight polyethylene for us. And the gentleman on the bottom left is my student, who's done all the work that I have presented here. He's now in University of Colorado Boulder, and he actually did experiments and theory and combination of all of these. It has resulted into a few patents and some very nice publications. So I acknowledge funding from both CSIR for Krishnadu and Reliance for funding this project. So I want to end here by saying that very nice industrial problems have very deep scientific understanding in them. So you not only get great patents, good papers, and a product in the market, but you also get very beautiful science that comes out of it. And as scientists, we all enjoy to publish and patent. So it all comes together. So this is one of those examples which I've thoroughly enjoyed, bringing polymer science and polymer chemistry together, and also an industrial application that emerged out of it. So thank you so much for your attention. I hope I have not bored you.
Thank you, sir, for the insightful lecture on the science that moves from change to change. And may I request Dr. Sarnan to facilitate our chief guest with a plate, please. Thank you, sir. May I request Dr. P. Kanikaveli, Chief Scientist at CSIR-CLRI, to propose the word of thanks.
Yes, small memento also given by Dr. Sarana, please.
respected Dr. Ashish, Director NCL, our distinguished guest, ladies and gentlemen. It is my great pleasure to express our heartfelt gratitude and appreciation on this occasion. On behalf of our director and also Dr. Saravanan, Chief Scientist, organizing and supporting staff, and on my own behalf, I extend our sincere thanks to Dr. Ashish Lele for readily accepting our invitation. And also, there was some changes in the dates because of the holiday, and we really thank you for accepting our invitation and delivering this wonderful Santappa-Raghavan Memorial Lecture, and also sharing a great knowledge on polymer science, particularly emphasizing how the molecular architecture and topology play a pivotal role in governing the melt rheology in polyethylene substances in relation to industrial scale melt processing. Our deep gratitude and appreciation to our former directors, Dr. Ramasamy, Dr. Chandrasekharan, and other guests, industrialists, alumni members from Alpha, CSIR family, and former colleagues, support staff, and students, and who have joined both in person and also virtually. Your presence and participation have made this event truly meaningful and successful. Thank you. We also gratefully acknowledge the support of the co-sponsor, the Lyric Trust, on this occasion. And finally, I thank our director for giving constant guidance, encouragement, and relentless support. Thank you all. Thank you.
Thank you, sir. May I request the audience to rise for the national anthem.
சொல்லுங்க. ஆமாம் ஆமாம் நான் உட்காந்துருக்கு சீட்டில்